Good morning, my name is Arturo Intellisano. I am a physicist, and even if I have studied quantum mechanics and the structure of the matter, I am been working in the field of space in the company Thales Alenia Space Italia since 15 years. I have been involved, and I am involved now also in the engineering of the satellite platforms. So everything which is usually called the bus, to distinguish it from the payload, which is the sensor or the probe which is mounted on the satellite to accomplish a mission. And in particular, I am avionics expert. So I am in the discipline which concerns the attitude, control and orbit and navigation, the data handling, the electrical power subsystem and the powering of the spacecraft. My lesson concerns a strange matter, which is information management in space. It is quite exoterical, said like that, because it is not in the standard topic that you can find in this discipline, but is a way that I have decided to introduce to see how it is important in the space discipline to convey technical and engineering matter at systemic view. And systemic means also how the information flux passes throughout all the segments and all the elements which typically constitutes a space system. The conceptual macro division of a space program is usually that you have a ground segment, for the example, the ground control station, the network which link more ground station, the engineering group which control through the ground station the mission objectives. Then we have the space segment, which is the satellite or the number of satellites which constitute the flying aspect of the space program. And then we have the system, which is the end-to-end concept which links together the two ground and space segment in order to accomplish the mission. Obviously, this subdivision is very macro in the sense that entering inside each segment we find additional subdivision in a very complex way. For example, we can, for the ground segment, have a lot of links, fiducial networks, ground stations which are necessary to link together all the visibility station which speaks and gather information from the satellite, and the user stations which ask for a specific target. Just to make an example, if we speak of low Earth orbit satellites, typically, for example, radar satellite or optical satellites, we have satellites which round the Earth in something about 1.5 hours. Obviously, it is not exactly like in a geosynchronous orbit, where you have the spacecraft continuously on visibility. So you have to have a link with your satellite only for a few minutes during its visibility in order to gather its telemetries and eventually to command the maneuver to control it. This means that to optimize this, you, for example, have to put in place more stations on ground to augment this visibility, or eventually you have to augment the autonomy of the satellite in order to enforce the possibility that it accomplishes its task also where not in visibility. The same subdivision concept concerns the space segment, typically, as I said before, divided into payload and bus, and then we have the subsystem, the thermal mechanical subsystem, the structural subsystem, the propulsion, the electrical propulsion subsystem, the avionics, the telemetry and telecommand. Inside the avionics, again, sensor, actuation, control laws inside the onboard computer. So I am just focusing on these different levels of segmentation to let you understand that it is very important to fix in a clear way how the informational flux among all these entities flow each other and which are the constraints and the problematics linked to this flux. Typically, subsegment engineer, a specialist, focuses only in his discipline. So there is the structure mechanic discipline that has gained some requirements from the top level project manager, and then it merges this requirement in his discipline. The same is for the avionics, for the system itself. The problem is to be able to make engineering having in view all the general aspects of the mission, even if this is typically the topic of the system engineer. It is important to broaden this view in order to make good engineering during the project. So, which is the link among these disciplines? I am speaking generally about information. Information is a very abstract matter in terms of semantics and also semiotics, but things started changing when Claude Shannon, in his seminal paper, started to give a precise engineering definition of what information is. The strength of Shannon definition goes beyond what he intended to do at the beginning. He was completely focused on telecommunication, but the definition it gave is so general that it could be applied in a more spread view. Starting, for example, from the concept of information entropy. In his famous, very simple logarithmic definition, we see immediately which are the basis of its definition. We see that there is a probabilistic assumption inside. We have a probability P, and this is strange. No one started to consider information, which is what exactly we transmit in terms of a probabilistic concept. And again, we see the two basic pillars of the information problematics, the probability and the constraint in the informational flux. We typically have an information source, a transmitter, then a receiver, then the destination, the final destination target of the communication link, and obviously among all these actors then can happen some noise which can disturb the communication itself. When we say that we have a transmitter and a source and a destination, we are speaking of physical means, and physical means are limited by definition. There is a problem of registry which code the information, so they are limited. There is a problem in the transmitting means, whatever it is, which is physically limited. You have a bandwidth, for example, in case of radio frequency transmitting. So, information is which are the constraints of the system and which is the probability, given this constraint, to gather the correct information. We are not speaking of semantics. So, the message itself the information which is coded and translated by other means is not the matter of Shannon definition. It could be in a way considered limitative because too much, let me say, crude. But indeed is, as I said before, it contains all the basic elements to address the topic of this matter when we put together different communication systems. So what is information exchange and how it is mapped on a space system? As I said before, it is usually analyzed at the specialist level, which can be inter-segment, inter-unit, at component level. Every member of an engineering team just focuses on one aspect of this discipline. But when we have to put together all the elements to assess which is the main design driver of a project, which are, what are the budgets, the schedule plans, the design issues of the dimensioning, we have to consider which are the constraints in terms also on informational fluxes. And when the system, like a space system, becomes too much complex, it is difficult to assess a standard methodology, let me say a metric, to see if we are really balancing all these topics in the correct way, and especially what information means in this field. The starting point to enter this subject is to see how the information is mapped and constrained in a space system. So, considering how the space segment communicates with the ground segment, for example, we usually add a telemetry and telecommand mean. In this topic, we have housekeeping information, which gather information about the satellite status. From the satellite, we have also that exchange for what concern the payloads. So we have some probes, we have some sensor. They gather information from the space and they transmit all this information to ground. Then we have a telecommand to control, as I said before, the satellite. And then we may have also direct link among the ground stations to put information together, for example, for a post-processing, or to have a better view of how the same information is seen from different ground stations seeing the same satellite. I make you an example. In the GNSS field, which is the field in which you use satellites for navigational and positional purposes, typically the GPS system, you have a satellite which take the information from the GPS constellation itself, process in real time this information to have a first definition of its position and velocity with a certain accuracy. If the same satellites are seen from a ground station and the same ground station takes the same information from the satellites, it is possible to combine all this information together in order to better and enhanced accuracy, both in terms of position and velocity. And this accuracy can augment of 1 order or 2 order of magnitudes. This is because, obviously, there is a limit in the space segment, as I said before, a limit in the mass memory and a limit in the processing capabilities of the onboard computer of the spacecraft. There are limits coming from the space environment itself, So for example, you have ionosphere degradations. You have multipath degradation for what concerns the radio frequency signal, and so on. The possibility to see the same scenario also from ground station, to put together all this information with the batch filtering schemes, to be able, for example, to remove systematic errors, like, for example, with the differential techniques, give you the possibility to enhance the accuracies. So the information flux among ground and space at system level enhance the overall information about the topic that in this case is the position of the satellite itself, and eventually also the geolocation, for example, of its sensing on the ground. There are also in these games some problems, for example, for what concern the antennas themselves, the fact that they are also affected by noise, by constraints on their dimension, for example, the fact that the diameter of the ground antenna is 5 meters or 7 meters and so on, and also the radio frequency band that you have used. In this topic, the number of ground stations plays a fundamental role. This is an example of Earth observation program, which is based on a radar antenna, which maps the Earth from a sun-synchronous orbit and requires at least 3 stations to accomplish its mission. So, the ground station visibility, as you can directly see from this image, is quite limited. The range of visibility for each station is represented by the white circles that you see mapped on the geoid. And for sure, on all the periods in which the satellite is not in visibility, and is the majority of the time, the satellite itself must be able not only to accomplish the standard mission, but eventually to solve the troubleshooting that can happen for whatever reason. For example, because of the failure of a unit. The antenna capability and in general the sensor capability is another topic which constrains much the information. In that game of visibility with the ground station which we have seen before, we have to consider the field of view by which the antenna really maps the target, and eventually also the ground station for the communication. And this target depends from the orbital altitude, the cross-track and the long-track distances, as you, for example, can see in this picture, and this depends on the fact that the Earth moves itself. The satellite also can perform some altitude maneuvers. The antenna has its own possibility to make, for example, steering to be able to gather a target. So this is another constraint for the information. And one of the major is the computer and mass memory limitation. Electronics in space is a complex matter. The space environment is a very harsh environment, especially in terms of radiation. This radiation changes in terms of altitude, so you have different figures according to the semi-axis of your orbit, to the inclination, to the eccentricity, to all the Keplerian elements you consider. So you can have less harsh environment, for example, in terms of absorbed radiation if you are in a low Earth orbit situation. But as long as you get higher with your altitude, passing from a MEO to a GEO orbit, things becomes more and more complex. And the problem is not only in terms of absorbed radiation, but also in terms of proton, in terms of heavy ions. So the cost of a space system are so high also because we usually are forced to have radiation hardened electronics in order to accomplish a reliable and long-term mission. So things changes if you have a mission that has to last only 1 or 2 years. But for example, typically a geostationary satellite for telecommunication can stay in orbit 36,000 kilometers for about 15 years, and it is exposed to very harsh radiation that at electronic level cause a lot of problem. Single event upset problems or latch up. So problems which can go from a sudden change, for example, in the memories, which can cause a jump in a processing, a reset of a computer or a mass memory, but can go also in more critical aspects. In the latch up you really change, for example, the CMOS technology characteristic of a component. There are also some strange phenomena, for example the whiskers, that has been seen in some commercial component when these commercial components were used for space. So a sort of epitaxial phenomenon has created some strange connection among resistor, capacitor, and so on, with the complete destruction of the electronics of the entire unit in which they were mounted. So you understand that the use of this component is expensive because it is expensive the way in which you create and design them, so in terms of fabrication, but also in terms of qualification of these components. In this picture you, for example, have a test setup for processor which must be exposed to heavy ions. In fact, microprocessor, ASICs and FPGA are particularly sensible to these radiations, and the cost for having radiation hardened components of this type is very high, in the order of €1 million for the qualification, for the realization, and so on. You understand that for the future, when we speak of cost reduction, when we speak of possibility of using commercial components, the trade-off on the architecture, which limits also the capabilities of this component, is quite a big problem. And again, they are key for the information, as I said before, so it is key to understand how much can be processed on board the satellite and how much can be processed on ground, because the satellite, because of this limitation, is not able to perform all the computations. There is another constraint, which is the physics knowledge we have about what we have to realize. This is a quite philosophical matter, but at the end we have a theory, better or not formalized. We have an empirism in which the reality is measured on ground or even from a return of experience of flight where are possible. And then we have to perform a trade-off given those limitations for designing our system. We are used from Illuminism to express our knowledge and our information in closed form equation. After the computer revolution, we put on the table also the numerical models. But in a sense, obviously, we just make a mix of our major knowledge areas, so the mechanics typically, the electromagnetism, the information theory, the statistics and the thermodynamics. These are basically the areas in which we move for a space system design. It is difficult to enter in strange discipline, at least up to the moment. As I said you before, I'm a quantum physicist, so I have not up to now exercised this matter in a space system, but who knows in the future. In any case, we have a picture of our knowledge in the space, and we have to trade off this picture with the design itself at project level, given the limitation I said before. Now, there is something that must be said in order to how the mathematical models and the physical models are used. We know that we send our satellite in a harsh environment from many points of view, as I said before, from a radiative point of view, but there are matters also linked to gravitational aspect, to solar flux activities, to also physics that we still do not completely know. So every project is based on the information we have to accomplish the task. What is the role of mathematics in this? Mathematics is a very powerful tool, especially because it gives us in a very synthetic way a lot of information on a particular perspective. Obviously, being synthetic, sometimes it is very difficult to include in a mathematical formulation all the aspects which constrains really a physical space system. We again speak of models, sometimes of different models, and it could be difficult to match all these models together. This is quite an art that the space engineering can have or not. But what is difficult is to put together all the elements that really make a space system effective. I make you an example. Let's see the famous standard Keplerian problem. The Keplerian problem in its formulation in the field of real numbers is very simple. You can see that in the real numbers field you have just a second order differential equation, and eventually in the second member you have all the additional forces which perturb the system. Very simple to see. But when the second member is not at zero, like in this case, and we have to really say what is the f, the function which is somehow perturbing the system, we enter in a very difficult discipline. It is difficult because, as I said before, the force can be third body problem, solar fluxes, gravitational anomalies, magnetic problems, whatever can influence the standard dynamics of a motion of a spacecraft. And so, even if it is very synthetical, it is hiding a profound problem to be treated really in a closed form, by pencil and paper, I mean. There have been, according to the discipline, also transformation of this perspective. For example, just to make an example, if we go from real numbers to complex number, you see that that same equation takes a different form, which resembles an harmonic oscillator. So indeed, the strange effect is that just going from the real numbers to the complex number, a very famous and complex equation like the Keplerian problem becomes a a more familiar oscillator, harmonic oscillator, that all the engineers and physicists know, because it is more intuitive to be treated, is one of the basic of the physics. Is we remind that Galileo started many of his consideration seeing the oscillation of a pendulum. And again, if we go in a third dimension, if we make an additional theoretical step going to quaternions, we have an harmonic oscillator in the quaternion in 4 dimensions, let me say, in 3 dimensions, but using quaternions, which are a sort of generalization of complex numbers. So just to say that also the mathematics itself changes if we change its perspective. The same formula seen from different fields of the mathematics, real numbers, complex number, quaternions, gives us different information. So again, it's a language. It's a very useful mean to synthesize what we know. It is quite schematics because in the attempt to enclose in a single formula all our information, we can lose or not other information, or we gather or not information according to the mathematics we use. So again, is an instrument, and as an instrument it must be used. It must not be confused with reality. Another classical approach, for example, is the Hamiltonian approach, where it's powerful. Unfortunately, there are not so many practical examples in which a complete Hamiltonian formulation is able by itself to solve all the problematics of a physical problem. But it is good at least to understand the complexity of the problem that we are facing. For example, in this equation, the V, which represents the potential which perturbs our Hamiltonian, we can have a lot of terms for defining the gravitational potential, starting from the simple 1 over r Newtonian potential, adding more and more terms to take into account the fact that the gravitation is not homogeneous, because the Earth has not an homogeneous distribution of mass, and that there are also other effects and so on. So there are a lot of techniques, typically perturbative techniques, to accomplish to this matter in order to increase the accuracy. The message is, when we use this mean, we have immediately an idea of the complexity of the subject, how much we can really control by pencil and paper, which is the complexity of our system, but is not all the history. It's fundamental to use this and to have in mind this typically at academic level, because mathematics is a trade union, a fast trade union to have an immediate way of on what road to take. You start with this, especially in the phase 0A of the project, so the first phase is when you start considering which are the problems, and you immediately have the idea of the real efficacy of a thinking, of a process. I have made a very simple example, the Keplerian problem, which is not simple at all. For example, the field of application of the so-called regularization techniques here exposed, you must know that they are very much used in astrophysics, for example, where we have many bodies and we have to perform big and complex calculations avoiding collisions. So this perspective is particularly useful for that kind of problem. It is less useful when you have a problem of define a very precise orbit propagator around the Earth, for example. At least up to now, it is quite a seminal part of this topic.